Hello and welcome back. In this lecture, we are going to look at a new technique for sorting. This is called merge sort. Here is a quick recap of some of the relevant topics we have already studied. We have seen what the sorting problem is. We have also seen some motivating examples, and we have looked at in some detail at a particular sorting technique called selection sort. We have tried to understand the intuition behind selection sort, seen a C++ implementation of it, and also did a very crude and high level analysis of its performance. In this lecture, we are going to look at a new sorting technique called merge sort. Specifically, we will look at the intuition behind merge sort and we will look at some animated examples. Now recall the intuition behind selection sort. We had an array of integers which was unsorted and we wanted to get them in a sorted order. In particular, if you recall, we wanted to get them in a decreasing order. So the way we went about doing this, start with the unsorted array and then solve a very small part of the problem. Specifically, we found out the maximum element in this unsorted array and put it in its rightful place in the sorted array. Once we had done this, we were left with a similar but simpler problem to solve. Why was it similar? Because we still had to sort the remaining marks. And why was it simpler? Because we had one less marks to worry about. So you see, the overall principle here is to take a larger problem and sort of break it up into slightly smaller problems. In this case, we found out the maximum element in the given unsorted array and then we got a slightly smaller subproblem in which we did not have to worry about that maximum element. Now this general principle is actually a general paradigm in computing. When we are given a large problem to solve, oftentimes we can solve the problem by decomposing the original large problem into several smaller subproblems. If each of these subproblems are themselves instances of the same larger problem but perhaps with reduced size of the input, then we can solve each of these subproblems separately and often using the same techniques that were used to address the larger problem. And finally, once we have solved all of the subproblems, we have to combine the results of these subproblems to obtain the solution of the overall larger problem. So this technique, this overall principle keeps appearing several times in different computational techniques, and in general this is called the paradigm of divide and conquer. We divide a large problem into several small subproblems such that we can solve these problems, and by solving the subproblems and combining the results, we can tame the difficulty of the original larger subproblem. So let us see if we can actually sort a given array of integers using this notion of divide and conquer. So here is our array of 6 integers which is unsorted and we are required to sort them. So what we could do is, we could say, well, instead of sorting an array of 6 integers, let us first divide this original problem into 2 subproblems where each is an array of 3 integers. So here I have just taken the top 3 integers in this column and formed the first array over here, and I have taken the bottom 3 integers in this column and formed the second array. So now I can say that, well, instead of sorting this larger array of 6 integers, I have these 2 smaller subproblems, and can I sort the first half of the array and the second half of the array independently and separately, and somehow can I combine the results of these simpler subproblems to get a solution of the original problem. So basically I would like to sort this sub array into its sorted order, which in this case happens to be the same as the original order, and I would like to sort this sub array by some means into its sorted order. Here it is sorted in decreasing order, and of course here you see that some changes have happened. 27 went to the top and 25 came down. And once I have these 2 sorted subarrays, notice that I just can't put one subarray by the side of another subarray and expect to get a sorted array of size 6. Indeed, this is a sorted array of size 3, this is a sorted array of size 3, but when I put them together, I may not get a sorted array of size 6. So I will have to do this additional step of combining these 2 results. So we will call them merging 2 sorted subarrays to get one sorted array of size 6. So what were the steps that we used in the technique that we just discussed. We took an array of size n and we divided it into two subarrays of size roughly n by 2. Of course, you would note that if n is odd, then the two subarrays will not be of exactly the same size, but their sizes may differ by 1. Now this is really easy to do. We can find the middle index in the entire range of indices of our array of interest, and then we can look at one part of the array from the beginning index up to the middle index and the other part of the array from the middle index up to the end index. Once we have divided the array into two subarrays, we wanted to sort each subarray of size n by 2. Well, how would we do this? Are we going to employ selection sort to do this? Well, I would say let us just wait for a few slides. We will actually see a very elegant way of doing this, but for the time being, let us just assume that we somehow can magically sort these two subarrays of size n by 2. As we have already seen, just having the two sorted subarrays does not help us in getting the original sorted array. So we have to merge these two sorted subarrays, each of size n by 2, and now of course the question comes, how do we do that? So let us first look at how we might merge two sorted subarrays, each of size n by 2. So here I have two sorted subarrays, each containing 3 elements, both of them are sorted in decreasing order, and what I want to do is I want to merge them and find one sorted array of 6 elements where the elements are sorted in decreasing order. How might I go about doing that? Well, I could have an index which points to the current maximum element in the two subarrays, and then I could check which of these two elements was larger. In this case 27 is greater than 24. So therefore, since this is the largest element in this subarray and that is already greater than the largest element in this subarray, so therefore this must be the largest element in the entire array, and so I can now put it at the topmost position in the entire sorted array. Once I have done that, I can increment my pointer or my index to point to the next highest element in this sorted subarray. While that index stays where it was, we have not yet been able to transfer this number to the sorted array yet. So now I am going to compare these two elements, since 25 is greater than 24 and these elements are already less than or equal to 24 over here, therefore 25 should occupy the next position in the sorted array, and this index now comes down and points to 24, and once again I have to compare these two elements. Now it turns out that 24 is not really greater than 24, 24 is indeed equal to 24. So now I have a choice of either choosing this or choosing this, but let us say for the time being that I am choosing this. So this element now comes down from that array and occupies that next position, and of course this index comes down over here. Now I am looking at this part of the subarray. I have already dealt with that element and I know this part is sorted in decreasing order, and I am also looking at this final part of the subarray which is also sorted in decreasing order. So I look at the topmost elements which are the maximum elements in these subarrays that I am looking at, and here it is 18, here it is 24. Since 24 is greater than 18, the next element to go should be this 24, and then I have now come out of the range of indices of subarray 2, which basically means I have seen the entire subarray 2. So all I now need to do is to take the elements from subarray 1 and just put them in the same sorted order as they appear in subarray 1 in the final sorted array. So this finally gives us the merged sorted array over here, and I have seen both these sorted subarrays. I have examined all their elements and placed them in their rightful place in this merged sorted array. So this is the way in which we could take two sorted subarrays each of size n by 2 and then merge them into one sorted array of size n. How would we go about sorting each of these subarrays? This was a problem that we had said we will look at slightly later. So let us now see how would we go about solving this. Well, if you think about it, we were actually trying to sort an array of size n, and now this problem says I have to sort two subarrays each of size n by 2. So why not try the same steps that I was going to use to sort the array of size n to solve each of these subproblems? Basically what I am saying is, can I recursively sort each of these subarrays by the same method? Well, the moment I talk about recursion, I have to worry about the termination case, and in this case the termination case is easy. When I get an array of size 1, that is this exactly one element in the array, then of course the array is sorted and I do not need to recurse any further. So this now tells us how we might actually employ a divide and conquer strategy to sort a given array of unsorted integers. So we start with the array of unsorted integers, divide it into two parts, get two similar but simpler problems. To solve each of these subproblems, I again divide it into two parts. Note that there are three elements, so these two parts will not be of the same size. One of them has one element, the other has two elements. And now if I look at this subproblem, it has only one element, so I have hit the termination case, the array is already sorted. For this subproblem, it is again divided into two parts, and once again this array has just one element, so it is the termination case. This other array also has just one element, so it is the termination case. So now I have sorted these two subarrays, in fact sorted them trivially because they had just one element each, and now I must merge them back together to get a merged sorted array of two elements. So in this particular case I get this merged sorted array, and I already had this merged sorted array from earlier, so now I must merge them together to get this merged sorted array. So that is what I get here. And now I must still solve this similar but simpler problem. So once again I will have to divide it into two parts, and now this part is an array of size 1. So I hit the termination case, the array is already sorted. For the other part I have to divide it further up into two arrays each of size 1, but then because this array is of size 1 I have hit the termination case, the other array is also of size 1, I have hit the termination case. So now I have these two sorted subarrays, I can merge them together to get this merged sorted subarray. Here is the other merged sorted subarray, I can now merge them further to get this merged sorted subarray, and finally I have to merge these two sorted subarrays to finally get the overall sorted and merged array. So finally we have our sorted array, and in fact this technique that I just showed by means of an animation to go from this unsorted array to this sorted array is also called merge sort. You would have noticed that merging two sorted subarrays was really the key step in this technique, and hence the name merge sort. So in summary, in this lecture we looked at the intuition behind a new sorting technique called merge sort. In fact, merge sort is basically a divide and conquer approach, and this naturally leads to a recursive formulation, and we also saw the very important role of merging sorted subarrays when doing merge sort. In fact, that is the key step in merge sort, and that is why the sorting technique is also called merge sort. Merging is the main step in this process. Thank you.